This is Programming Chapter 6, Part 1. We're going to be looking at array concepts. As we've talked about before, arrays make accessing a lot of data more efficient than allocating individual variables. And a common thing to do with lists is to sort them. We frequently have alphabetic lists, but we can also sort lists numerically, such as standings in a sports league. And we're going to learn two simple algorithms for generating sorted lists, bubble sort and insertion sort. It's always important to understand how efficient an algorithm is when it's sorting and for accessing. There are more efficient sorting algorithms, but they're complicated to implement. And we'll be using the standard libraries after we learn about data structures. We'll start with insertion sort. We're going to sort in ascending order, but it's just as easy to do a descending sort. An important property for sorting is the ability to sort in place. This means we don't have to duplicate the array to sort it. And when you're using large arrays, you don't want to duplicate it because it takes extra memory and extra execution time. And fortunately, insertion sort has this property. We're going to use a small list, but the concept extrapolates to larger lists. And what we have below is the list after each major iteration. We start off with the list in this order. And the first iteration, we don't do anything with the first number because there's nowhere to move the first number. So we start off with the second number. This is the second number. However, the index is 1. The index here is 0. Be very careful when you're counting, otherwise your algorithm won't work. So when you're looping, you want to start this loop at 1. So the idea here is we save this. This spot will get overwritten depending on the comparison. So we check to see if 16 is less than the previous number, 8. It's not, so we just store 16 back into this spot. And that's the first iteration. We don't do anything with this. Next iteration, we save the -3. And we look at the previous number. Remember, this index is 2 now. We're looking at index 1. We're comparing to see if it's less than 16. It is less than 16. So we move 16 into its spot. Now we're pretending that the -3 is here. It's not, but we're pretending. And we compare to the next value at index 0. Is it less than 8? Yes, it's less than 8. So we move the 8 into its spot. Now we're at 0. We can't move any more left, so we've saved it, and we just put it in index 0. Okay, now we're at 4. Again, we save this value. We compare it to the previous index, 3. We compare it to the previous index, which is 2. It's less than 16, so we move the 16 into its spot, index 3. We're at index 2. We compare to the previous value, index 1, and it's 8. It is less than 8, so we copy 8 into its spot. Now we're at index 1. We're comparing to index 0. Is it less than -3? No. So we take the save value and put it into index 1. And then we repeat. So with 11, we move the 16, store it in its 16 spot. Last time through, we have 4. It's less than 16. It's less than 11. It's less than 8. It's not less than 4. So we take its value and put it into index 2. So once we put it in the spot, we terminate. We don't do any more comparisons. We go on to the next iteration. And that's the last iteration. So just a note, the first array element is index 0. The last array element is index n minus 1. So we don't have an index n in an array. So your first exercise is to implement this algorithm. You're going to have to iterate backwards through the list. You're going to download exercise 6.1 if you need to see how to do this. And if you download this exercise, all you have to do is insert the correct condition to complete the sort. And if you do nothing with the comparison, it simply reverses the list. And here is the example. And let's put a breakpoint here. And we're going to run it. Okay, let's just take a look at the output window. It just prints the original list. You should leave this list to make sure that your algorithm works properly. It'll be easier to debug with this list than if you tried to use some other list. Okay, so we step through. And we see that we're starting at index 0. We save the element. We start j at 0. And while j is greater than 0, it's not greater than 0, so there's nothing to do. We just put the element back into its original spot. And we print the list. You can take a look at the list. It's identical. Next iteration. We grab the 16. We save it. And here you're supposed to do a comparison. And right now it's just going to move the 8 up. And it's going to decrement it. And now it's 0. So we're done. We take the 16 and store it in element 0. And we print the list. Take a look at the output. Okay, unfortunately I ran the whole thing. You can see that it's moved the 16, it's moved the -3, it's moved the 4, it's moved the 11, so it's just moving everything because there's no condition. And finally the 4 gets put at the beginning, so it's reversed the whole list. Once you put in the correct condition, it will sort properly. And exercise 6.2, you're going to use the same exercise, but make a copy. And then you're going to do a descending sort. And a quick note about the efficiency. So in the first loop, we made 1 comparison. In the second loop, we made 2 comparisons. In the third loop, up to 3 comparisons. So each time we go up, we're incrementing the number of comparisons. So 1 plus 2 plus 3 plus 4 plus 5. So we have up to 15 comparisons. This is 6 times 5 divided by 2. There are 6 columns and 5 rows. If we say the list size is n, we have n times n minus 1 over 2, which is n squared over 2 minus n over 2. It's okay if you don't know how we derive this, but you do have to understand that this is the biggest term, n squared over 2. And for efficiency, we just ignore the leading coefficient, which is a half here. So the efficiency is just order n squared. So n squared, we just write n squared like that. However, the best sort routines have an efficiency of O n log n. This LG version of log means base 2. In general, we'll only use insertion sort for small lists, that is, n less than 100. If you don't care about efficiency, you can even go up to 1,000. If we look at a list size of 100, this is roughly 100 times 100 comparisons versus log n. This is 100 times 7 comparisons. So 100 divided by 7 is roughly 14 times slower. If we have a list size of 1,000, the number of comparisons is 1,000 squared versus 1,000 times 10. 1,000 divided by 10 is 100 times slower. So if you have large lists, insertion sort is not the way to go. If we go to Desmos, so we can look at x squared and x log x. Again, LG is log base 2, so we have to do log x divided by log 2. You can see that this red line is growing a lot faster than the blue line. And the gap keeps getting wider and taller. And we can zoom out. And you can see the efficiency just doesn't compare. So that completes this part of Chapter 6. You'll go on to do bubble sort in Part 2. And that completes this lesson.